In this video, I'm going to go over some examples of vectors in 2 and 3 dimensions. Recall that a vector is a mathematical object with both a magnitude and a direction. We represent a vector by an arrow, where the length of the arrow tells us the magnitude, and the arrow itself tells us the direction. Let's start with the first example. Given vectors u and v, we can think of those vectors as illustrated on the screen. Find the vector of 2u minus 3v. I'm going to work out this example in two different ways. First using the triangle rule, then using the parallelogram rule. Now the vector 2u has the same direction as u and twice the magnitude. And the vector minus 3v has the opposite direction as v and 3 times the magnitude. So let's start by drawing the vector 2u. Same direction as u, twice the magnitude. Here's the vector 2u. The vector minus 3v has the opposite direction of v and 3 times the magnitude. If we're using the triangle rule, I'm going to position the vector 2u and minus 3v so that the initial point of minus 3v coincides with the final point of 2u. So with that said, we draw 2v minus 3v as follows. This is minus 3v. Notice how I positioned the initial point of minus 3v to coincide with the final point of 2u. Now the resultant vector 2u minus 3v would look like so. It is the vector whose initial point is the initial point of 2u and whose final point is the final point of minus 3v. So that's 2u minus 3v. Now let's work the same problem, but this time we'll use the parallelogram rule. So I'll start by drawing 2u and I'm going to position minus 3v so that its initial point coincides with the initial point of 2u. So here is minus 3v. Let's complete the parallelogram spanned by 2u and minus 3v. And the resultant vector 2u minus 3v is the following diagonal. This is the vector 2u minus 3v. Notice it gives the same result as when we apply the triangle rule. Compare the two vectors, or compare the vector 2u minus 3v. In both cases, you'll see that we're ending up with the same result. A vector with the same magnitude and direction. Next example, Given point P with coordinates -2, 3, and point Q with coordinates 4, 7, write the vector PQ in component form and find the magnitude of vector PQ. The vector PQ has two components. The first component is as follows. It's the x-coordinate of Q minus the x-coordinate of P. And the second component of vector PQ is the y-coordinate of Q minus the y-coordinate of P. Hence, the components of PQ are 6, 4. On to the magnitude. The magnitude of vector PQ is the square root of 6 squared plus 4 squared. That's the square root of 36 plus 16. That's the square root of 52, which is equivalent to 2 root 13. Next, let's find a unit vector in the direction of the vector v with components -3, 5, 1. Well, the vector v divided by the magnitude of v is a unit vector in the direction of v. So let's find the magnitude of v. That is the square root of -3 squared plus 5 squared plus 1 squared. That's equal to the square root of 9 plus 25 plus 1. That's equal to the square root of 35. Now we take the vector v and divide it by that magnitude. So we have v divided by its magnitude. We simply do this component-wise, meaning we divide each component by the square root of 35. And we get that the vector with components -3 over root 35, 5 over root 35, and 1 over root 35 is a unit vector. You can check that it has magnitude 1 and has the same direction as v. Next example, let v be the vector with initial point 3, 4 and terminal point -5, 2. Express the vector v as a linear combination of the standard unit vectors I and j. Recall that the standard unit vector I is the unit vector with components 1, 0, and the standard unit vector j is the unit vector with components 0, 1. To solve this problem, let's start out by writing the vector v in component form. To do that, we're going to do the coordinates of the final point or terminal point minus the coordinates of the initial point. So v has first component -5, -3, and second component 2, -4. This means the vector v has components -8, -2, which we can write as -8 times the vector with components 1, 0, minus 2 times the vector with components 0, 1. You can easily check this by using the rules of addition, subtraction, and scalar multiplication of vectors, which is essentially done component-wise. So that's equal to minus 8i minus 2j. And that's the linear combination of the vector v in terms of the standard unit vectors I and j. This next example deals with direction angles. Find the direction angle theta of the vector v equals 3i minus 4j. Well, the direction angle is determined by tangent theta which is the y component of v, that's minus 4, divided by the x component, which is 3. This means that theta is tangent inverse of minus 4 over 3. We can get this answer with a calculator and make sure the calculator is set in degrees. That's minus 53.13 degrees. In a picture, it looks like this. Here's the x-axis. Here's the y-axis. The angle is minus 53.13. The minus tells us to go clockwise. And here is our angle, minus 53.13 degrees. This is the vector v. But by definition, the direction angle of a vector v is going to be the counterclockwise angle from the positive x-axis to the vector v. So really, the direction angle of v is not minus 53.13, but rather it is this angle here, which is coterminal to minus 53.13. What I illustrated in red is the coterminal angle. How do we obtain this angle? We simply take minus 53.13 and add 360 degrees to it. So I'm going to write here to finish the problem, since the direction angle of v is the counterclockwise, I'll abbreviate it with CCW, angle from the positive x-axis to v. We have theta is really minus 53.13 plus 360 degrees equals 306.87 degrees is our direction angle. Another example with direction angles. Find the direction angles of the vector v with components 1, 2, 3. The vector v is three-dimensional, so it has three direction angles, alpha, beta, and gamma. Let's write direction angles of the vector v. These are alpha, beta, and gamma. All of these angles are in the interval from 0 to pi. Alpha is the angle in the interval from 0 to pi between the positive x-axis and v. Beta is the angle in 0 between 0 and pi between the positive y-axis and v. And gamma is the angle in 0 pi between the positive z-axis and v. These direction angles, alpha, beta, and gamma, are determined by the following three equations. Cosine of alpha is the x component, which is 1, divided by the magnitude of v. The second equation is cosine beta is the y component of v, which is 2 divided by the magnitude of v. And the third equation is cosine gamma. That's the z component, or the third component of v, that's 3, divided by the magnitude of v. Let's find the magnitude of v. That's the square root of 1 squared plus 2 squared plus 3 squared. That's equal to 1 plus 4 plus 9. That's the square root of 14. We have everything we need to find the direction angles alpha, beta, and gamma. So cosine alpha is 1 over root 14, which tells us that alpha is cosine inverse 1 over root 14. Using a calculator and making sure the calculator is set in degrees, this gives us roughly 74 degrees. Cosine beta is 2 over root 14, which means that beta is cosine inverse 2 over root 14. That's roughly 58 degrees. And finally, cosine gamma is 3 over root 14, which means that gamma is cosine inverse 3 over root 14, which is roughly 37 degrees. Another example with direction angles. A vector v makes an angle alpha equals pi over 3 with the positive x-axis, and an angle beta equals 3 pi over 4 with the positive y-axis. Find the angle gamma that v makes with the positive z-axis, given that gamma is obtuse. To solve this problem, we're going to capitalize on an equation that relates the cosines of the three direction angles alpha, beta, and gamma. We write the direction angles alpha, beta, and gamma, they satisfy the equation cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. We know that alpha is pi over 3, so we have cosine pi over 3 squared plus beta is 3 pi over 4, so we have cosine 3 pi over 4 squared plus cosine squared gamma equals 1. Cosine pi over 3 is 1/2, so 1/2 squared plus cosine 3 pi over 4 is minus 1 over root 2, so minus 1 over root 2 squared plus cosine squared gamma equals 1. That's 1/4 plus 1/2 plus cosine squared gamma equals 1, which means that cosine squared gamma is 1 minus 3/4. That's 1/4. So, cosine squared gamma is 1/4, means cosine gamma is 1/2, or cosine gamma is minus 1/2. Recall that gamma has to be between 0 and pi. So solving the first equation, cosine gamma equals 1/2, means that gamma is pi over 3. And solving the equation cosine gamma equals minus 1/2 yields gamma equals 2 pi over 3. But we're given that gamma is an obtuse angle, which means it has to be strictly between 90 degrees and 180 degrees, or between pi over 2 radians and pi radians. Therefore, the correct answer is gamma equals 2 pi over 3. So I'll end the problem by writing, since gamma is an obtuse angle, gamma equals 2 pi over 3. Final example is an application. It's an application from physics. A 100-pound weight hangs from a string as shown in the figure. Find the tensions vector T1 and vector T2 in the string. To solve this problem, I'll start out by introducing coordinate axes as follows. Here is the x-axis, and here is the y-axis. Now I'm going to look at all of the forces acting on the 100-pound weight. To simplify the problem, I drew an easier figure, or a simplified figure, on the right-hand side of this screen. So we have 3 forces acting on the 100-pound weight. We have W, which is the force due to gravity. It's pulling the weight straight down. That's why I illustrated it as the green vector pointing straight down. We have a second force, which is the tension T1 in the first string. And the third force is the vector, or the force T2 in the tension in the second string. From the geometry of the picture, notice how the vector T2 makes 30 degrees with the positive x-axis, and the vector T1 makes 50 degrees with the negative x-axis. Now I'm going to write each of those vectors, W, T1, and T2, in component form. Starting with W, since it points straight down, it has no x component, and therefore the x component is 0. And the y component is negative 100. That is because the weight is 100 pounds and gravity is pulling it straight down. That's in the negative y direction. So the components of W are 0, negative, 100. Next, let's look at the components of the vector T1. That's the tension in the first string. If we take the vector T1 and decompose it into its x and y components, we see that the x component is negative and the y component is positive. The x component is the magnitude of the projection. Actually, it's the signed magnitude of the projection of T1 onto the x-axis. That is minus the magnitude of T1 times cosine of 50 degrees. And the second component of T1 is the signed magnitude of the projection of T1 onto the y-axis. That's given by the magnitude of T1 times sine of 50 degrees. Using a calculator, we see that cosine of 50 degrees is roughly 0.64. So the first component of T1 is then minus 0.64 times the magnitude of T1. And sine of 50 degrees is roughly 0.77. So the second component of T1 is 0.77 times the magnitude of T1. Now let's look at the components of T2. Notice that both the x and y components are positive in this case. T2 is the signed magnitude of the projection of T2 onto the x-axis. That's the first component. And the second component is the signed magnitude of the projection of T2 onto the y-axis. So the first component of T2 is going to be magnitude of T2 times cosine of 30 degrees. And the second component is the magnitude of T2 times sine of 30 degrees. Cosine of 30 degrees is root 3 over 2, which is roughly 0.87. And sine 30 degrees is, of course, 1/2, so we'll write it as 0.5 times the magnitude of T2. Now we have all of our vectors, or all of our forces, in component form. Let's continue. We have the picture again on the right-hand side of the screen, and we have our vectors, or our three forces, in component form. One thing about these three forces, W, T1, and T2, is that they are in equilibrium. Simply, they balance each other out, and therefore the sum of these three forces must equal the zero vector. So we'll write that vector W T1 and T2 are in equilibrium. This means that the vector W plus the vector T1 plus the vector T2 equal the zero vector. When we have the vectors in component form, we simply add them by adding the corresponding components. So to find the left-hand side of my vector equation, I'm simply going to add the x components of the three vectors and then add the second component, or the y component, to get the second component of my left-hand side. So we have 0 minus 0.64 times the magnitude of T1 plus 0.87 times the magnitude of T2. What I did here is I added the x components of the three vectors. Now I'm going to add the y components. We have minus 100 plus 0.77 times the magnitude of T1 plus 0.5 times the magnitude of T2. I added the second components. This is the left-hand side. The right-hand side is the 0 vector, which has components 0, 0. And we know that two vectors are equal if and only if their components are equal. So this last vector equation gives rise to two equations, namely 0 minus 0.64 times the magnitude of T1 plus 0.87 times the magnitude of T2 equals 0. We'll call that equation 1. What I did here is that I simply equated the first component of the vector on the left with the first component of the vector on the right. The second equation is minus 100 plus 0.77 times the magnitude of T1 plus 0.5 times the magnitude of T2 equals 0. We'll call this equation 2. And to get this equation, I simply equated the second component of the vector on the left with the second component of the vector on the right. Again, we have two equations. 0 minus 0.64 times the magnitude of T1 plus 0.87 times the magnitude of T2 equals 0. We call that equation 1. And minus 100 plus 0.77 times the magnitude of T1 plus 0.5 times the magnitude of T2 equals 0. We call that equation 2. I'm going to use those two equations to solve for the magnitude of T1 and the magnitude of T2. From equation 1, I can solve for T1 in terms of T2 as follows. So look at the equation and solve for T1 in terms of T2 to get magnitude of T1 is equal to 0.87 over 0.64 times the magnitude of T2. And if we plug that into equation 2, we get the following. So plugging in to equation 2, we get minus 100 plus 0.77. Now instead of putting T1, I'm going to replace T1 with the following expression. That's going to be 0.87 divided by 0.64 times the magnitude of T2 plus 0.5 times the magnitude of T2 equals 0. This is an equation in the magnitude of T2. We can solve for T2 to get magnitude of T2 equals 64.64. And we can go back here and solve for the magnitude of T1 to get 87.87. Finally, let's find the tension T1 in the first string and the tension T2 in the second string. At the beginning of the problem, we found that T1 has components minus 0.64 magnitude of T1, 0.77 magnitude of T1, and we found that T2 has components 0.87 times magnitude of T2, 0.5 times magnitude of T2. We also found that the magnitude of T1 is 87.87 and the magnitude of T2 is 64.64. So I summarized all of this information right here. If we plug in the magnitude of T1 for T1, we get that the tension T1 has components minus 56.23 and 67.66. This is done by plugging in 87.87 for the magnitude of T1. And if we plug in 64.64 for the magnitude of T2, in T2 we get that the vector or the force T2, which is the tension in the second string, has components 56.23 and 32.32.